Hello everyone, we are here for performing our tutorial 1.2 electronic OLED simulation. As per previous discussion, we have already performed 1.1 tutorial OLED simulation. Who has not seen it, please check out the playlist. Before we start our tutorial electronic OLED simulation, I want to introduce myself. I am Sahil Verma, Application Engineer of the well-known company Impulse Technology. For more detail, check our company websites impulsetechnology.in. We will be perform our tutorial Setfos tool, which is developed by Fluxim company. Now we move to next slides. Before directly jump on performing tutorial, we should be know about what are we going to exactly perform. As here, electronic OLED simulation, it is the optimized organic light emitting diodes. OLED are a type of LED that use organic compound to produce light when an electrical current passes through them. They are used in many devices including TV, phone and computer monitors. In this tutorial, we are going to simulate that constitute number of the layers as gold anode, MEH layer and calcium as a cathode. We will be simulate at here pulse operations and analysis the transient current. We will be shift the applied voltage and calculated current voltage curve of device. Finally then we will be build an opto-electronic coupled model. Now we are going to perform our tutorials electronic OLED simulation. It is a Setfos. Now you will be click at right sides and run as an administrator. It is a new feature of Setfos 5.5 as here new dropping models are introduced. The new version of Setfos 5.5.4 as given here you can study at per your demand. For the create new simulation file you can click at create new simulation file. As we have already studied about geographical user interface of Setfos, if you are not aware about it, please check my playlist. For create new simulation file, you can click at here create new simulation tool. It is a layer structure given here. It is a whole of the geographical user interface as we have already studied at tutorial 1.1. As per name of tutorial electronic OLED simulation and pulse operations analysis the transient currents. With all of these, you are able to make sense that we are going to calculate here electrical properties. So we will be click here battery look-like symbols drifted fusion module for calculate electrical properties. So we will be activated that module. You can see here drift fusion settings available here. In here layer structure, I will be give one by one all the layer name. You can add more layer at the plug symbol. You can click at here calcium. Now you will be give the thickness of all the layer. As we know, top and bottom layer are semi-infinite medium, so thickness are irrelevant here. Gold thickness consider 10 nm, MEH PV layer consider 120 nm, calcium it also consider 10 nm, subtract will be a 100 mm. It will be a now I will be define gold as a anode. You can see at here layer structure as per thickness it will be changed. Click at the tab as a now I will be define gold as a electrode, thermionic, organic and work functions consider 5.1. MEH PPV layer we will be defined as a semiconducting by activating the corresponding in general settings. At here you will be see HOMO and LUMO energy level have already mentioned at here. You will be import MEH PPV electrical mechanical properties. It is a format of .em file. Now you have imported MEH PPV file. We will be define now calcium as a electrode, thermionic organic injection model. Work function will be considered 3.3. We will be notice at here semiconducting layer in between of gold and calcium. Both are electrode. We will be simulate the transient response to a applied square pulse signal as diffusion settings tab have already activated. We will simulate the transient response to an applied square pulse signals. We will be click at drift diffusion setting tab and transient response at the mode. You can check at here journal steady state solver transient signal transient solver. At in the transient signal we click at here and enable transient electrical. So we can check at here number of the segments list given at here, steady state level and custom voltage given at here. Transient signal is defined by sequential list of signal segment of different types. We will be define a square signal by three constant signal. The top element of the segment list is steady state. So transient simulation of Setfos always start from steady states. As custom level voltage, consider it will be a zero voltage. You can add number of the segment by click at the add segments plus symbol. We are defining at square signal by three constant signal. So I am considering at here three segments. At the first segment I will consider zero level and duration it will be a 50 microsecond. And the second constant segment I will consider at 4 level and duration is 100 microsecond. Similarly at third segment it will be taken as constant level, it will be a 0 and duration consider 150 microsecond. As we have mentioned three of the segments, it means device will stay at 0 volt steady for 50 microseconds before it is pulse. As total time simulation 300 microseconds, so it will default as auto. Note that total time for the transient simulation is defined by the length of the transient signals. You can see at here total transient signal. It will be at here 300. Start from the 0. It is square pulse signals. Now we will be go at transient solver and see at here numerical tolerance. Numerical tolerance as already mentioned at here, it generally means your answer it is most closest at that value. Post transients at the time steps it will be considered 5 microseconds. It is already enabled flexible output time steps. So all of the your settings as completed at here. Layer structures, semiconducting properties of MESPP layer, drift diffusion settings. So now you will be give name of your file. Simulate pulse current operation. You can give at the simple name as simulate pulse current operation. Now I will be run that simulation. You will be get all of the results. As the time steps, you can see it here. Current balance transient, device current transients, device current vs voltage, power density transients, and the reflected it will be look like dark blue. All of the properties you can check at here result view. It is a editor view. You can edit value as per your demands and run the simulations. Changes automatically occur. All of the data given at here. So I am here simulate pulse current operation. Now I am going to simulate current voltage curve. In the drift diffusion settings, you will be click at here and the mode you will be change at steady states. And the steady state, its solver, it consider as auto as already given. Now I will be shift over an applied voltage. Activate the shift modes. Setfos automatically jump to the shift setting tab. The range and discretization is given from to and a step value also mentioned at here. Now I will be consider at here voltage. As we are going to shift voltage, its range consider from 2 to 10 and step it will be taken 0.1. Unit it will be already given at here. Voltage you can check at voltage and millivolt, you can taken as per your choices. So at here shift settings have completed. Now you can run that simulation. You have already given a name here. Now run at play button. Electrical properties given at here: built-in voltage, current balance, device current, power density, band diagrams. It is all of the electrical profiles mentioned at here: charge density, currents, electrical field, mobility, potential, recombination, absolute residual error, iteration, residual error, passive optic properties, CI transmitted, color refractive index, reflected color, solar integrated, reflectance, psi, stacked contributions, and transmittance. As device currents, you can see at here current and voltage curve. It is J, recombinations and language. You can change at here color as per your choice. Line, you can change at here dotted, circles, triangle. For the log profile, you can click at here. You can change at y-axis also. For the shift, you can give the value at here and it will be shifted around at x-axis and y-axis as you want. Now I am going to perform electronic to optical coupling. We will solve drift diffusion equation and use the calculate excitation distribution as emission source for the optical light coupling. For the optical coupling, emission mode must be activated. So we will be click at here bulb symbol for the activate emission mode. To calculate light out coupling, we must specify the reflecting index of the material. So firstly, we will be imports gold refractive index. At the tabulated NK file format, we will be import gold. It is a tabulated NK file. We will be select and we can check at here preview. Similarly for MEH PPV file, we will be import at here that do MEH pv.nk file format. Select it and import. You can check at preview at here. As similar calcium, import calcium.nk file format and selected and check at preview at here. It is a line emitting layer, so we will be activate at the general tab emitter. We will be activate emitter tab. So at here you can check emitter 1 given at here, and we will be now imported photoluminescence spectrum file. The file format supported at here .pl, so it is given at here. You can see at here .pl file format and given name at here photoluminescence spectrum. Now you will be select and you can check at here luminescence spectrum preview. Intensity at the y-axis, wavelength at given x-axis. Enable the coupling between excitron and dipole. Select at distribution excitron coupled. As you can see at here excitron dot 1. This tells Setfos used to calculate exciton distribution as source of the dipole. All the excited parameters like diffusion constant, radioactivity decay, like that, defined in electrical material file as .em.file format. In the case they can found in do.meh.pv electrical mechanical file as we have already stored. Go to the drift diffusion settings and activate the checkbox at the general tab of the excitation. We will be enable that exciton tab. Now you will be able to calculate of all the calculation of the exciton. So now all of the settings you have already done, like layer structure, emission setting, drift diffusion settings, shift settings and output settings as per your demand. So now you can give new name as per your choices, and otherwise you can run the simulation. Now you can give your simulation name electronic OLED simulation and run as simulation. It is sweeping all of the parameters. Now your results are given here. All of the electrical integrated properties, electrical profiles, emissive properties, numerics, optical integrated, electrical, passive optics properties, spectral, and spectral emissions given at here. Edge emission you can see at here. Click at the right sides, copy all the curves. You can move that voltage and press the voltage button. You can see at here emission data. You can also give name at here as per your choices for the better understandings. For more data, you can copy at here. For the voltage graph, you can check. As I have already told, x-axis, y-axis, and you can zoom at here, and the emission spectrums for the S polarizations and P polarization. So now I have completed my tutorial 1.2 electronic OLED simulation. If you have any query about it, please drop me a comment, and also you can email at given my description box. You can also check my company websites impulsetechnology.in. Thank you very much.